I guess this topic we're going to talk about is registration and normalization, and the idea concept is basically putting all of your lesion imaging data into one common space. So that's going to be that's basically what I'm going to be talking about for the most part. But before I do that, I do want to sort of step back and go back to the beginning. So far, we've been discussing a lot of background and a lot of theory, things like what is VLSM, introduction to Linux, intro into registrations, lesion segmentation and tracings. But now we're going to actually sort of put all these steps that basically everyone's been learning into practice and see how it actually really works. So, stepping back, we're going to look at 8 steps, VLSM basically in 8 steps. So we're going to go through step 1, which is renaming and converting Diacoms, how to downsample, doing the radiologic neurologic flip, segmenting. I'll go back and talk a little bit about that. Then go into registration and normalization, which is the bulk of what I'm going to talk about. I'm going to speak also a little bit about quantizing, merging lesion file, and then last, running the stats. Oops. Okay, so we're assuming that basically you've gone through, you've gotten your scan, and at some point you have some kind of Diacom files, whether that's through the whether they're clinical files, this is a clinical scan, or you went to the scanner and you have your research protocol of some sort. But basically, you're going to have a big directory of Diacom files, which, if you've ever looked at them, it's a series of numbers. It doesn't make sense. It's really kind of difficult to work with. So Voxel has a really cool command, which you can use. It's called VB rename. And if I just type that and give the input as the directory with all my Diacoms, it'll go through and sort all of my Diacoms into specific folders, which tell me which sequences associated with which runs, and basically it becomes a lot easier to work with, which it's doing right now. It's taking a little bit longer than I thought, but anyway. It's a large.
While we're waiting.
Yes.
So how does the program know, having looked at this big set of folders, how does the program know what is what?
It's basically reading the headers from the Diacom files itself, and basically sorting them into the different sequences that, wow, it's taking really long. Basically into the different sequences. So, like in this particular protocol, I know that we've run a couple of functional runs. There's flares, there's MP-RAGE, and a couple of other sequences. I think a flare as well. I'm not sure if I said flare. But if we now go into that, everything's been sorted into the different sequences of files that we have. So, and for our purposes, as far as VLSM is concerned, we're interested in the structural files. So depending on where you're getting your files from, right, it could say MP-RAGE, it could say structurals, it could say SPGR, all of these, or T1s, all of these are different names for this series of files that we're looking for. In this case, I'm interested in these ones, which are the MP-RAGE files. But if I actually go into that directory, you'll notice it's still a series of individual files, which represent, 1 to 160. It's still kind of difficult to work with. So the next thing that I want to do is just compress them into a single file, and we use the vbconv command. And if I just give it again, oops, the name of the directory and, what I want to call it, it's going to go through and give us a nice single file, which we can look at. Oops, actually, that's going to... It now has our lesion file, our structural image, basically. We can scroll through all through 1 through 60. After we've sort of sorted our Diacoms and created our structural file, the next step we typically want to do is to downsample our images. So as we talked about in the lesion tracing session, we don't want to have to trace depending on how big a lesion. And this person has a fairly decent sized lesion. You don't want to have to trace that many slices. So what you can do is basically downsample to cut down on the number of slices to trace. And to do that, I usually use I start off by looking at what actually, hello? Sorry. It's odd. We can use the VBI command to see, what exactly is the dimensions of our file, right? And with that information, I can then use another command in VoxBo, which is resample. I just tell it the name of the file that I want to resample, the output name, and I'm going to use the NN flag, which stands for nearest neighbor in terms of its interpolation. And then I can put -d and the actual dimensions of what I want it to be. So in this case, x is 192. I'm going to leave all the other dimensions the same, but I'm just going to cut the other in half. And
Olu or others,
yes.
Why resample just in the Z dimension and not in the others?
There's no particular reason. I mean, you could resample in all dimensions.
But that's because you draw in that orientation.
Yeah.
So you just define the number of...
Yep. I just define the number of slices in the Z dimension, to cut it in half, and basically I now have half the number of slices to trace. Right. So if you actually look at the slider here, you'll see that it goes to 80. VoxBo considers 0 an integer. Other programs like in Windows, 1 is actually an integer. So that's why it says, yeah.
Yeah, are you actually interpolating these slices, or is that just VoxBo naturally?
No, it.
Are we actually downsampling?
Yeah.
All the case with the -n flag, which means just take the nearest name, to find the nearest optical way.
Okay, so
if you leave that out, it's incomplete.
Yeah.
Thanks much for that.
Yes. All right, so you now have basically a downsampled series to be able to work with. The next thing is, if you notice, and we've kind of talked about this before, our file is in radiologic convention. It's nice. It's not necessarily nice that this guy has a lesion, but he does have a lesion, and we know it's a left hemisphere stroke. So we know what side is it on. But if you noticed here, it's on the right side. So we need to do a neurologic flip, basically, because our data is in radiologic convention. And to do that, I use the VBIM command. And again, I just give it the name of the file that I want to change, the -flip y, then write, and the output name that I want to give it. In this case, I'm just going to name it food.ni. Sorry, that's wrong. It should be X. Good catch. And if you now look at our file, we're now in neurologic convention. And this is going to be important because most of our atlases, like the Brodmann's map and the AAL atlas, are in neurologic format. If you're doing this with, without that are, excuse me, if you're doing this with your data from normal subjects, right, it becomes a lot harder to determine what's right and what's left. It's a sort of a good general assumption that, at least when you're working with voxel, that it's in radiologic convention when you initially use the VBCOM command to convert your files.
That's for that particular Diacoms format, right? Because last week I mentioned that whatever, right-handed, left-handed, flexible is not, can be flexible. Sometimes you can show on the right side the knowledge convention.
Yes.
It's worse than that. You basically have to know what comes out of wherever you're getting the images.
I was going to say, yeah.
So my question was, what in the Diacom format do you actually read out and then you show that into the reality convention?
I don't know.
We don't trust the orientation information in the Diacom file. The only actual information in the Diacom file that's relevant is probably the position of the person in the bore of the magnet, which in our case is always head first supine, which means they're on the back of the head with the center first. Beyond that, the Diacom file doesn't include anything about the position of the subject. Since that's pretty constant for us, we can pretty much ignore it. But I wouldn't, on general principle, if you're getting Diacom from elsewhere, I wouldn't necessarily trust them to always be correct.
Yeah.
Suggestion. You want to change your PowerPoint slide?
Yeah.
So, use that as a reference.
Thanks. Okay, so you've now done sort of the radiological flip. Next part is deciding what method you're going to use to segment or trace your lesion. It's going to be the painful, what we refer to as Wimbledon plus method. It involves tracing and repitching, or you're going to use the Wimbledon plus method, which we've kind of talked about, which is warping. And we still use the Wimbledon, I just want to make it clear that we still use the Wimbledon plus method for dealing with our CTs. Excuse me, yeah, Wimbledon, thank you, method for our CTs. And this is just to give you a sense of the difference in image quality between some our 3T scans, right, our CT images, and as with most of our CT subjects, they usually have some health precaution that prevents them from getting an MRI scan. And in this case, this person has a shunt, which clearly is sucking up half of the scan, as you can see. So a lot of it has to deal with just the coarse nature of the CT scans, that we're unable to warp them using the current methods that we have. But it's also the case that some people may choose to go ahead and do the Wimbledon method for MRIs. And I think before I had mentioned the MRI cron that it doesn't actually have pitch. That's actually not correct. If you actually go under Draw menu, Advanced, and do, Rotate. This actually then gives you the ability to change the pitch. For us, we've typically only done just changes in pitch, but you could do in the other planes like yaw and roll.
When you rotate it in MRI, does it rotate it around the center of the image, or does it find the origin, or how does it do it?
I think it pretty much rotates around the center. So, and in which case, if this was what we're actually going to use the method, right? You have your subject here, you have your column template here, and in this scenario, right, you'd be looking to click rotate, and you're looking to just change the pitch. Let's see if we can get it to go. It's a little slow, but you can begin to see that it's changing the pitch here. And you're, in doing this, right, you're looking for, as Grant described, matching up structures. Are you going to, how much of the cerebellum do you see at certain levels?